Hey guys, Miss Marusik here, and in this video we're going to talk about bond energy. Now, I know a lot of you remember that with ionic compounds we talked about lattice energy, the energy I would need to break apart an ionic compound. Well, bond energy is basically the equivalent of lattice energy, except now we're going to be talking about covalent compounds and things that share. So to kind of start us off here, they gave us this nice lovely little picture here and asked us some questions. And the first question it asked is what subatomic particles in different atoms would attract? Well, if I kind of look at the picture here, I notice that a nucleus of one particular atom is attracting to the electron cloud of another. Well, if we remember, in the nucleus we have protons, so what that means is that the protons in one atom attract to electrons in another atom, which makes sense because we know positives and negatives attract. Well, when I'm dealing with repulsions, you notice here that a nucleus that has positives is repelling another nucleus with positives. So protons repel protons, but also we notice that the electron clouds are also repelling each other because, again, they're both negative. So electrons repel electrons. So those like charges end up repelling each other. So here's the problem with covalent bonding. I have to ensure that these attractive and repulsive forces are basically balanced. If I get these atoms too close to one another, then what happens is that the repulsive forces kind of win out. But I have to at least have them a certain distance to each other so that they can attract to each other. So it's almost like I've got to find this sweet little balance between attractive and repulsive forces. And that's where bond length comes into play. So there's a little statement down here that I kind of starred just because I feel like it's a really good summary of kind of what has to happen here. It says that the most ideal length of a bond for covalence is where the attractive forces between unlike charges, so the electrons and the proton and the nuclei, are balanced by the repulsive forces between like charges in the electron-electron repulsions and the nucleus-nucleus repulsions. So again, we're trying to find this sweet spot for a bond where attractive and repulsive forces are balanced out. So with that said, scientists created kind of a graph to represent where this sweet spot is at. That sweet spot is going to have a particular bond length to it, which, by the way, remember, bond length we more formally call internuclear distance. And then we're also going to have an energy associated with that optimal distance. So you notice here on this graph, along our x-axis here, we have our internuclear distance, or interatomic distance here, as they've called it, and then we have our energy. So what I have right here are two atoms that are really far apart and they feel no attraction. Now, to kind of show you what's going on in this graph, I actually have two magnets that I'm going to use that actually, conveniently enough, are spheres. Okay, so what's happening here is that those spheres are so far apart that there's no attraction between them. But as I start to bring them closer and closer together, at some point they're just going to naturally feel some attraction. And so when they do that, they reach this optimal distance apart from each other. Now you notice a dip here in energy as that took place. That is because we kind of maintain that ideal energy associated with this. And when the bond forms, that frees energy when I form it. So we're going to have a very specific dip associated with each and every bond. Each and every covalent bond has its own energy dip that takes place. Now, what's happening here is if I try and press these any closer together, now obviously these being solid spheres, that's kind of impossible, but if I try and press these any closer together than that ideal distance, what happens is that our nuclei and our electrons are getting way too close with each other that the repulsive forces start to take over. And so it doesn't want to come any closer together. I would have to put in a ton of energy to push these any closer together than they already are. Okay, so this is my ideal distance here. Now, you notice the energy did dip because it released energy when that came together. We're going to talk about in thermochemistry a statement that says takes to break, frees to form. So I freed energy when I formed that bond. But let's say I wanted to break that bond back apart. Okay, because that attraction is there, I'm going to have to put in quite a bit of energy to pull those apart to then let them go on their merry way. So I have to input energy there in order to break them back apart. So here's the deal. If you notice, there's another chart down here that basically looks the same, except this chart is specifically for hydrogen. So here's where my elements are starting really far apart from each other. I'm going to start to bring them closer and closer together, just like I did with those magnets. And at some point, that energy is going to dip to an optimal level. You notice here it says it's a negative 432 kilojoules per mole for hydrogen. So that's how much energy is released when those elements come together. And you notice that has a particular internuclear distance associated with it. So for hydrogen, that bond length happens to be 74 picometers. However, if I try to bring those any closer together than 74 picometers for the internuclear distance, I would get a lot of resistance because of all the repulsion. So trying to push them any closer together would take a huge input of energy to bring them together. But not only would it take an input of energy to bring them together, but if I wanted to bring them back apart, if I wanted to break that bond, I'm going to have to put in some energy as well into that. So you notice on this graph, they mentioned here the energy released when bond forms. So that's going down. But then here, the up is the energy absorbed when the bond breaks. That energy right there is our bond energy. Okay, so to give us a definition down here, I said that bond energy is the energy required to completely separate 1 mole of a covalent bond into its elements. Now, I will warn you, as many of you know, energy is sometimes called enthalpy. So if you ever see a textbook reference it as bond enthalpy, it means the same exact thing as bond energy. They're not really any different, okay? And if you notice, it's pretty similar to what we saw for lattice energy for ionic bonds. Obviously, lattice energy is breaking up into ions, whereas here, I'm just breaking up into neutral elements. So there's a few differences there, but the idea is it's how much energy it takes to break those bonds. So it says, as with lattice energy, an increase in bond energy indicates higher, or you could say stronger attractive forces, and also a stronger bond. So surprise, surprise, the more tightly our things are held together, the more energy I would have to put in order to break that bond. Also, it says, keep in mind that when a bond breaks, the energy is absorbed. I have to put in that energy to get it to break apart, as we mentioned, meaning the process is endothermic and should technically be reported with a positive value. A lot of times you'll just see it without a sign altogether, but if they do include a sign, it should be positive for this one. All right, so with that said, just like we saw with lattice energy, we are going to see some variables that could affect our bond energy values. Remember, with lattice energy, we talked about magnitude of charge and internuclear distance as our 2 factors that impacted lattice energy. Well, with bond energy, we're going to see some of those same things affect us. Now, big difference is that I don't have ionic charges for covalence. So the charge is going to be kind of done in a different way. When you're thinking about Coulomb's law and that charge over distance, charge for covalence is going to look a little bit different. So here's what I want you to do. There are 4 questions right here that all have to do with this lovely table right here. So what I want you to do is to take a moment and pause the video and see if you can answer those 4 questions. All right, so pause the video. Go answer them. Did you answer them? I'm going to guess that you did. I'm going to assume that you did. So with that said, let's look at what I put, and you can see if maybe you put something very similar to me. All right, so the first question said, hey, looking at the top half of this table right here, make a statement that relates the relationship between bond length, aka internuclear distance, and bond energy. Well, I had chlorine to chlorine, bromine to bromine, iodine to iodine. You notice chlorine to chlorine was our shortest bond, whereas the iodine to iodine was our longest bond, and we'll talk about why here in just a minute. You also notice that the shorter the bond, the higher the bond energy. As that bond got longer, the bond energy got a lot less. So, as bond length increases, bond energy decreases. Well, let's think about that for a minute. Bond length is internuclear distance. So as the distance gets bigger, what would happen to attractive forces? Well, the distance gets bigger, attractive forces should decrease And so it should take me less energy to break up that bond. So on the second bullet point, it said, hey, make a statement that states the relationship between moving within a group, occupied energy levels, internuclear distance, attractive forces, and bond energy. Holy macaroni, they mentioned a lot, and I'm so sorry because they didn't leave us a whole lot of space to do that, right? Well, chlorine to bromine to iodine, if I look at that on the periodic table, I'm like, okay, here's chlorine, here's bromine, here's iodine. They're in the same group, and so as we know, each time I move down, I'm going to gain an occupied energy level. Chlorine, being in period 3, should have 3 occupied energy levels. Bromine will have 4, and then iodine will have 5. So I add on that occupied energy level each time. So as I move down a group on the periodic table, my occupied energy levels increase, okay? Which we know that having those extra energy levels means that the internuclear distance would also increase. As distance increases, our forces decrease, and so the bond energy decreases. So surprise, surprise, I think probably a lot of us could have kind of predicted that one before we even answered these questions. However, the second part of this is kind of interesting. It says, hey, looking at the bottom half of the table up above, make a statement that relates the relationship between the number of shared electrons, attractive forces, and bond energy. So looking at the second half here, you notice here they're showing carbon to carbon with a single line, carbon to carbon with a double line, and carbon to carbon with a triple line. So that is indicating a single versus a double versus a triple bond. Well, if you remember back to when we discussed bonding in pre-AP, a single bond would be sharing 2 electrons, a double bond would be sharing 4 electrons, whereas a triple bond will be sharing 6 electrons between those 2 elements. So what that means is as the number of shared electrons increases, as I went from 2 to 4 to 6, the attractive forces increase, okay? Because if there's more shared things, we're going to be holding things more tightly together. And we can see that that bond energy would increase. So where with ionics, we talked about ionic charge playing a role, here with covalence, the number of shared electrons is going to play a role instead. So on this last question here, it says, hey, do we see more fluctuations in bond energies due to atomic radius differences or due to the number of shared electrons? Well, let's look. We notice these first 3 were differences in radius, and we see some variance here, about 100 kilojoules per mole of difference between the biggest and the smallest. But look at the differences here between the single and the triple bonded carbon. We notice a difference of almost 500 kilojoules per mole. So a lot more difference in bond energy when we're dealing with those shared electrons than when we're dealing with just adding energy levels. So think back to lattice energy for a minute for ionics. With lattice energy, remember how we said that charge trumps distance? That charge was more important to look at than the number of occupied energy levels? Well, the same holds true here. Here, though, the shared electrons trumps distance. So the shared electrons are what we want to check first. And then if the shared electrons are equal, then we can look at occupied energy levels. So thinking back to Coulomb's law here, force equals charge over distance. So when we are dealing with a covalent, our charge piece of this is going to be the shared electrons, and the distance is still going to be that internuclear distance. I kind of abbreviated their ID for internuclear distance, okay? All right, we got 2 questions down here that we're going to answer together. So the next one says, rank the following bonds from highest predicted bond energy to lowest predicted bond energy. So first, I'm just going to kind of write these out and kind of go from there. So I'm going to have P bonded to F. We're going to have N bonded to F, and we're going to have O bonded to F. And it says, again, rank from highest predicted bond energy to lowest predicted bond energy. Okay, well, first off, we notice that they only drew 1 line between each of these. So what that means is that I have single bonds here. So shared electrons is going to be equal for all of these. So I can kind of take that out of consideration. So what that means is that now I want to think about internuclear distance. So I want to kind of think about my radius of these things to decide what should have a bigger or smaller internuclear distance between these. So with that said, I'm going to kind of go look at these elements on the periodic table. First off, I notice they all have fluorine. So that piece of internuclear distance is going to be consistent. So I really here care about the phosphorus versus the nitrogen versus the oxygen. So here's my phosphorus, here's my nitrogen, and here's my oxygen. Well, first off the bat, I see, hey, phosphorus is in period 3. So that should have 3 occupied energy levels. 3 occupied energy levels. I'm going to abbreviate here. While as these other guys have 2 occupied energy levels. Okay, so off the bat, I already know that this guy here is going to have the largest internuclear distance. That's going to be the biggest, right? If I have the most occupied energy levels there, then that's going to be the largest. Now, on the other 2, I kind of have to use my noggin here. Think about nitrogen versus oxygen. Yeah, they're in the same period, so they have the same occupied energy levels. But think back to atomic trends. Oxygen has more protons, which means its effective nuclear charge is greater. And if that's greater, then it's going to have a slightly smaller radius than the nitrogen. So if it has a slightly smaller radius than the nitrogen, then that means it's also going to have the smallest internuclear distance. Again, the fluorine's the same in both of those. So this guy here is going to have the smallest internuclear distance. Okay, so with that said, let's think about that now. Larger the distance means that I am going to have weaker forces. Which means that this one here should have the lowest bond energy. On the flip side, this guy with that short internuclear distance, with those atoms really close to each other in the molecule, then here my forces should be the strongest. And so here I'm going to have the greatest bond energy. Okay, so it said, hey, rank these from highest predicted bond energy to lowest predicted bond energy. So we did that. It also said, hey, which one would be considered the strongest covalent bond? Well, that's going to be the oxygen to fluorine. That has the strongest forces, and so therefore it'll be the strongest bond. Weakest covalent bond, on the other hand, will be this guy here. If it had the largest internuclear distance, it would have the weakest forces, and so therefore be the weakest bond. And we've already addressed the bond energy as far as the greatest and least. And so hopefully you kind of feel a little more confident with doing something like that. Again, if you also introduced the number of shared electrons being different with these, then that would be something we would need to look at first before we did these internuclear distances. Okay, so with that said, we got one more question down here. And you notice here what they've done is they had given us one of those bond energy graphs. And what they want us to do is to sketch in another curve for a different element. So it says here, hey, this right now is a graph for Br2, which, by the way, to kind of help us out here, Br2 has a Lewis dot structure that basically looks like this. It is a single bond between them. So that's not going to, be a double or a triple or anything like that. And then it asks, hey, what would the graph look like for Cl2? Well, chlorine being in the same group, his Lewis dot structure is almost going to look exactly the same. He's also going to have a single bond. So here's the deal. Shared electrons are equal for both of these. So yet again, guess what I want to look at? I need to look at that internuclear distance, which means I need to kind of evaluate my occupied energy levels here. So I'm going to go to bromine and chlorine on my periodic table. And again, I see that bromine has more occupied energy levels than chlorine does. So if chlorine here has less occupied energy levels to it, then that means it is going to have stronger forces. It's also going to have a bond length, an internuclear distance that is shorter. Okay. Last but not least, let's talk about the energy. Okay. If we said it has less occupied energy levels, so it has those stronger forces because it has a shorter internuclear distance, then what that means is it's going to have a really high bond energy to it in comparison to the bromine. So if this curve was for bromine, and I now want to draw in chlorine, remember, this part of the curve is energy. Well, we just said that the chlorine is going to have a bigger bond energy to it, which means this dip needs to be more significant. Remember, that dip shows as I go up how much energy I would need to gain to break it. So the bigger the dip, the bigger the bond energy. So I need a dip that is lower than this one. But I also need to address the bond length. Now, I know they didn't label this axis on here, but the internuclear distance is along this axis right here. That is our bond length. And so, as we said, we want that bond length to be shorter. So that also means I need to shift my curve over this direction a little bit. So what that means is when I draw in my chlorine curve, I want to make the dip lower and more to the left, to show that its internuclear distance is a little bit less than the bromine. By the way, you're going to see some similar differences in these graphs if you had something where the shared number of electrons was different. So keep that in mind, that these graphs can shift either because of occupied energy levels, our internuclear distance, or they can also shift because of the number of shared electrons. All right, hopefully you're feeling a little more confident with bond energy, and we see the similarities it has to lattice energy. Again, they're kind of the equivalents of each other for the two different types of bonds. If you have any questions or need any help, please feel free to email me. Bye, guys.